So when we have a repeated game, so for example, if we had A to be 0, 6, 1, 1, 7, 5, and B to be 0, 3, 1, 1, 1, 0, and we have identified the best responses, which in turn of the stage games, and let's say we're repeating this twice, so our repeated game is that, but we have the stage game and we identified two Nash equilibria. So 0, 1 and 1, 0, 0, and 0, 1 and 0, 0, 1. Well, if we want to find a Nash equilibria for this repeated game, a straightforward one is to realize that actually any sequence of stage Nash equilibria is a Nash equilibria. So if I use the notation R1, R2, and C1, C2, C3, we see that we then have four Nash equilibria, which are R2, R2, and C1, C1. And this is just compact notation, right? But we can still say that this is a mapping of strategies, of histories to strategy to actions. And then if we have R2, R2, and C1, C2, that's another one. And we have all four of them, right? So R2, R2, and C1, C2, C1, and finally R2, R2 with C2, C2. And just to be clear, this is C2, this is C1, this is R1, and this is, R2, and this is R2. Now, the fact that any sequence of stage Nash, so R2, C1, followed by R2, C2, for example, which would be this one. The fact that any sequence of stage Nash is also a stage Nash for the repeated game, that can be seen by just considering the game in its sequential form. So in essence, we have the game is played, and then we play the game again, right? And theoretically, as many times as we have t. But if we just had t equals 2, then we just have this. And now what we do to prove this is we actually look, so the game is played this way, but we actually look backwards, all right? And so we say, okay, once this has happened, so once we've played R2 and C1, do the players have any incentive to move in the final round? So given that the second player is going to play a stage Nash, should the first player deviate from the stage Nash? And the answer is no, because by the definition of a stage Nash, we're essentially just looking at the single game, so no player has a reason to deviate. And so once we know that, we then go backwards another step. And given that we know no one has a reason to deviate here, does anyone have a reason to deviate here? And we keep on going using backwards induction, and the proof follows using this inductive process. So that's a quick way of being able to identify something that's a Nash equilibria. And if we look at these particular Nash equilibria, we can compute the utilities. So R2, R2, and C1, C1 means we're here and here twice. So this has utility 2, 2, and this has utility 6, 2, this has utility 6, 2, and finally this one has utility 10, 2. But the interesting question arises is, okay, so these are sequences of Nash equilibria, of stage Nash equilibria, and they are Nash equilibria for the whole game. But is it possible to find a sequence, well, a particular strategy or a sequence of plays that isn't a sequence of stage Nash, but is a Nash equilibria for the whole game? And that's going to be the next thing that we see, and the answer is yes.